Hello everyone, my name is David Cardona, and this is my final project for 3D graphics with Professor Mike Shaw during fall 2020 at Harvard Extension School. My project expands upon the idea of terrain maps, except that I am not reading in the height, value, or y position from a texture file, but rather I am setting all y values to 0 and modifying them during runtime in the Vertex shader using a sine waveform. The first thing that happens is that the user will be prompted for the dimensions of the plane that they want to render, and then the parameters are passed. The conditions simply ensure that the largest parameter or the largest value is passed in as the first parameter, and the smaller value as the second parameter, which helps the parser. Inside of the terrain abstraction, in the absence of textures, the amount of x segments will be subtracted from the x value, and of c segments will be subtracted of the c value divided by 2, and this is so that the center of the shape is in the center of the screen. The y value is set to 0, and we are then adding our indices to the index buffer using add index instead of the make triangle method of the geometry abstraction. And this is because the make triangle method uses normal information, texture information, in order to calculate tangents and bitangents and create a normal buffer layout that uses 14 values. That wasn't necessary for this example, so I am simply generating a buffer layout with the position values that we calculated. The rest of the work is being done inside of the Vertex shader. In addition to this, the Vertex shader takes 13 point lights, which is an aesthetics choice, and it also takes in a directional light, which is moving. I'll soon show you how. The Vertex shader first defines all normals pointing outwards in the z direction. We then calculate the sign for the position, for the y position based on the x and c positions. Same for the normal. There are two render modes between the sign. Well, there are actually three render modes, but the third one is a flat plane, which can be seen right here, and this is used for debugging and making sure that all lights are placed in the right place. But the other two modes, which interact with the sine wave equation, the first mode will utilize only the first coordinate passed in this case is the x-axis coordinate, in order to calculate or do the sine wave calculations for the y value. And what this creates is a wave that is moving sideways from one side to the other. The second mode multiplies that value by the second coordinate as well, also scaled by the wave number value. And this results in a sine wave moving outwards from the center in two diagonal directions and moving inwards to the center in the other two diagonal directions. The directions of those diagonals are set on whether you are subtracting or adding up the angular frequency by the time and period. Time is what will make everything move, and the wave period is what will determine how fast everything is moving. The angular frequency in radians is what it's ensuring that everything stays within range, that everything is always scaled in such a way that time won't cause the sine wave to just keep getting closer and closer together and going faster and faster. Computing the TBN matrix in the absence of tangents was an interesting challenge. Since the normals are pointing outwards in the z direction, it was necessary to create a vector that was perpendicular to that. I am just using an up vector, which is pointing upwards in the y direction, and I am computing the cross product between that up vector and the normal component in order to compute the bitangent. More information on this rotation can be found in Mike Molisani's final project, where he implements tessellation and geometry shaders. I am then computing the tangent values for directional lights, point lights, the view position and the fragment position, and the movement in the directional light is created by using a sine wave and a cosine in the x and c coordinates respectively, and what this will cause is a circular motion around the y-axis. Sine will make it go one way and cosine will make it go the other way, so when they are both moving at the same rate it will result in a circle. All this information is taken in by the fragment shader, and the fragment shader is very similar to what we were using in the multiple lights examples and to what we were using in the normal mapping examples. Only big difference is that I am assigning my colors using HSV, hue saturation values, which takes in 3 parameters. Is another way of representing colors. First we have hue, which is what color is being displayed. Here is the saturation of that color, which is the second parameter, and the third parameter is the brightness. The brightness in this case is left at maximum in order for it not to darken too much, but the saturation and the hue value are being automated. Then scaled by 0.7 to give it a bit of a darker tone. And then I am using this function to convert HSV into RGB so that OpenGL can interact with that color value. The function can be seen here. And I did include a reference of where to find it. Now, if I run my program, first thing that will happen, I will be prompted for the width and the height of the screen, the X and C dimensions of my plane. In this case, I'll just pick 250 and 250 for easy access. It directly goes into the first mode of the sine wave. The other modes can be seen here. This is from the center, and this is a plane, which, as I said, is useful for light. The one from the center looks better as the peaks come closer together. This can be done by updating the wave number. I do have some key commands in order to control that. This is seen from above. It can be rendered in points also, which looks actually prettier. This is the view from the side, from above, below, forward, backwards, etc. I'll go back into top view in this sine wave example, only modified by one coordinate. I also have controls for increasing the wave period, which is a little bit jittery when I modify it, but it does result in the wave moving a lot faster. It will not bring the peaks closer together. That is done by updating the wave number value. So as you can see, everything is coming together, and I can also control the amplitude, which is how far these heights are departing from the y coordinate center, which, if you remember, is at 0. This was my final project. Thank you very much for watching. Please feel free to reach out with any questions you may have.